Now let's study about shock waves. To understand shock waves, let's first discuss a situation. Say we are given with an observer, and in front of observer there is a source of sound which is emitting waves of frequency n0, and say source is moving towards the observer with the speed vs. So we know well in this situation when a source is moving, its actual wavelength is compressed due to the motion of source. Now in this situation, if we find out the apparent frequency heard by the observer, this n apparent can be given as n0 c by c minus vs. This we have discussed quite in detail and taken several examples based on this. Now in this situation, let's see what will happen if the speed of source approaches to the speed of sound. Sound is traveling at a speed c, and say source will start traveling with the speed c, then we can say in this situation the source will be traveling with the equal speed with which the wave is propagating. So when one wavelength of sound is emitted from the source will also approach to this position, as the wave as well as source both are moving with the speed c. In this situation you can see if Vs is equal to c, this apparent frequency tend to infinity, and here we can see the apparent wavelength will tend to 0. So almost negligible wavelength waves are emitted or when this will approach to observer, the frequency will be almost infinite. Now in this situation, we can see the frequency and wavelength are becoming impractical, or this is practically very difficult to analyze mathematically. Let's understand what will happen in Doppler's effect as well as what will happen when the source speed becomes equal to c, or even when the source speed becomes more than the speed of sound. Now in this situation, let's understand first about the wavefronts produced by a point isotropic source which we already studied in the previous topic, that if there is a point isotropic source, it produces sound three-dimensionally in all directions uniformly. So in this situation, we consider the wavefront, which is the cross-sectional plane of the waves in which all particles oscillate in same phase. So a point isotropic source produces a spherical wavefront. So this is a spherical wavefront, and we can say that as the sound propagates in all directions from the source, the size of a spherical wavefront increases with the speed c. Now what will happen if the source starts moving? Say if source is at rest at a point, it will continuously be emitting spherical wavefronts, and the size of wavefronts will be increasing with the speed c, and source will be located at the common center of all these wavefronts. Let's understand what will happen when the source starts moving and how the wavefronts are produced due to the motion of source, or what will be the situation we can see when all wavefronts are observed simultaneously. Say we'll start with the effect on wavefront due to motion of source. Dear students, to understand shock waves in a systematic manner, we need to understand first the effect of wavefront propagation due to motion of source. Let's discuss a physical situation which we have just now discussed. Here you can see there is a source which is at rest and it is producing sound. So here you can see the waves produced by the source are propagating in form of spherical wavefronts. And as these spherical wavefronts are propagating, we can say the size of these spherical wavefronts will increase at a speed of sound, and your velocity of source is 0. This is the very first situation we have discussed. As just now we have seen, if the source is at rest, the spherical wavefronts will propagate in outward direction at a speed of sound c. Now let's discuss a case here when the source is traveling with a speed which is less than the speed of sound. Here you can see as the source is moving in forward direction and simultaneously it is also producing spherical wavefronts. So the distance between successive wavefronts in forward direction is relatively less than the situation compared to the case when it was at rest. And behind the source, the separation between successive wavefronts is more than the situation when it was taken at rest. So here you can see in this situation, due to the motion of source, the wavelength in the direction where it is moving is relatively compressed or less, and behind the source it is increasing. So due to which we can say the frequency in forward direction is relatively more, in backward direction it will be less. And we can also state the medium or the air in which the source is moving in front of the source, as the wavefronts are relatively closer, which are having oscillations in same phase, the air density slightly increases, and behind the source air density slightly decreases. This is quite an important concept to understand. Let's carry it further. Here you can see this is the still picture of what we have just seen, that separation between wavefront in front of the source is decreased and behind the source it is relatively more. And this is the situation when the source velocity is less than the sound velocity. If a source is traveling at a speed less than that of sound, this will be the case. And say if we consider a situation when source velocity is equal to sound velocity, then you can say source will always be located at the front end of the wavefront which is produced. So in this situation here you can see another realistic situation, that if the source is moving at a speed, here I can see if V is traveling at a speed equal to the speed of sound, if Vs is equals to V, or we can take it C also. In the first case I have taken the sound speed as C. So in this situation, if source speed is equal to that of the sound speed, you can see the source is always located at the front end of the all the wavefronts which it has already produced, and it is moving in such a way that in front of it the separation between successive wavefronts is negligible. And we can say when a source travels at a speed of sound, in front of the source, as the wavefronts gets very close to each other, the density of waves, density of the medium in front of the source is excessively high, which creates a resistive barrier for the source. And if say source will be having a tendency to increase the speed beyond this value, there will be a sudden jerk due to very high density of medium in front of the source. Now let's see the still picture for the similar situation here. In this situation, you can see as source is producing all the wavefronts, source will always be located at the front end of the wavefronts, as these wavefronts are expanding at a speed V or C, which is that of the speed of sound, and source is also traveling with the same speed. So it will always be maintained at the surface of all these spherical wavefronts, due to which here density of medium excessively increased, because of which source experiences a very strong jerk when it will be crossing the speed, or we can say when source will increase its speed beyond V, then it will experience a very high jerk, and this is called sound barrier. Now let's discuss what will happen when the speed of source is more than the speed of sound. Here we can visualize that if source speed is more than the speed of sound, then at every time source will come out of the previous wavefront which it has emitted. So these spherical wavefronts will be intersecting, and source will come out of each wavefront which it has emitted from the previous position. And let's discuss the realistic situation here based on that. Here you can see as source is traveling with a speed more than that of sound, new wavefronts it is producing when it comes out of the previous wavefront. And here you can see all the spherical wavefronts will increase their size with the speed of sound, and at any instant if we pause the situation, you can see the wavefronts are propagating in such a way that the common tangential plane of all these wavefronts will form a conical surface, and this conical surface can be regarded as the conical wavefront for the waves which are produced by the source when it travels at a speed more than the speed of sound. And these conical wavefront waves are called shock waves. Why these are called shock waves, that also we'll see. First, let's discuss the situation in slightly more in detail. Let us discuss in detail about shock waves. This is the still picture of the physical situation we have just now seen, and it happens when a source travels at a speed more than the speed of sound. So at every instant, source will come out of the previous wavefront when it has produced another wavefront, and this is the surface which is the common tangential plane of all these wavefronts, where we can say all these points are oscillating in same phase. So this basically can be regarded as conical wavefront of shock waves. Shock waves are also termed as supersonic waves, which are waves. We can also term these as supersonic waves. These are the waves which are produced having conical wavefront whenever a source of sound travels with a speed more than the speed of sound. In this situation, this conical surface is also called surface of Mach cone, and in this situation, if we analyze the basic geometry of the conical wavefront, we can say from initial position in a time t, the source will have traveled a distance vst, and in the same duration, this spherical wavefront would have traveled a distance vt. V is the speed of sound, and in this situation, if we talk about this right angle triangle, this angle is theta or this angle is theta. Here we can write sine theta is equals to Vt by Vst. In this situation, we can write theta as sine inverse of V over Vs. This is the angle made by the conical wavefront of shock waves with the direction of motion of source. Now in this situation, if the value of velocity of source is changed, obviously the angle will also change, and this particular conical surface or the conical wavefront is termed as Mach cone. And here, let's also discuss why we term these waves as shock waves. The reason is, within this conical region, if we consider a point x, we can say at point x there are more than one locations of the source from which simultaneously waves will arrive in same phase. When waves will arrive in same phase at a position on the surface of this cone when the wave is propagating, we can say the oscillation amplitude of x will be excessively high, because we already discussed when n waves superpose at a point in same phase, the amplitude of resulting oscillation becomes Na. So in this situation, we can say the intensity will be n square times the intensity produced by the source from one location at this point. And here n can be very large, so each point in the medium may have very high oscillation energy. So if there are some physical objects available in this particular zone, the oscillation of medium particles of that objects will enormously increase and the object may shatter or break down. And that's why such waves which are having very excessive energy are termed as shock waves.